Today we are going to learn about changes of state. We have three states or three phases of matter, and according to the kinetic particle theory, when the solid particles gain heat, the particles vibrate faster, increase in volume, expands, forces of attraction becomes weak, and the regular pattern is broken. In this process, the solid changes into a liquid. The solid starts to melt, so the process is named melting. Then, if the liquid gain more heat, the energy of the particles increase, the particles move faster, and some of the particles at the surface have enough energy to overcome the forces of attraction, and they escape to form a gas. So the process by which the liquid changes into a gas is called evaporation or boiling. When gas particles lose energy, the gas starts to condense. So condensation process turns into a liquid. When liquid particles lose energy, they start to freeze. So the process by which the liquid changes into a solid is called freezing. From solid to liquid to gas, energy is put in or given. From gas to liquid to solid, energy is given out. Some substances change from the solid state to the gaseous state without passing through the liquid phase. This process is named sublimation. So, sublimation means the process by which the solid substances changes into the gaseous state without passing through the liquid phase. Examples of some materials that sublime. The first example here is iodine. Iodine is an element used in pharmaceuticals and disinfectants. The second example is dry ice, and dry ice is the solid form of carbon dioxide. The third example is the naphthalene, or we call it mothballs. The fourth example is ammonium chloride, and it's used in fertilizers. So, materials that sublime change from the solid state to the gaseous state without passing through the liquid state. Some important points regarding changes of state. We took water as an example. Ice turns into liquid water. Liquid water turns into water vapor or steam. Regarding changes of state, is a new substance is formed? No. So no new substance is formed. In other words, we call this a physical change. We have here ice, which is H2O. Water is H2O. Water vapor is H2O. So no new substance is formed. The second point is that changes of state is a reversible change. What do we mean by a reversible change? We know that the solid turns into a liquid, the liquid turns into a gas. Reversible means we can get back the liquid, we can get back the solid. So from solid to liquid to gas, and from gas to liquid then solid. So this is a reversible change. If we have liquid water, we can turn it back into ice. If we have water vapor, we can turn it back into liquid water. So this is the meaning of reversible. The third point is that changing of a state doesn't affect the mass of the substance. How is this? We have here ice, water, water vapor. Here water, H2O, water. Here ice H2O, water H2O, water vapor H2O. So the mass is not affected. The mass doesn't change. The differences between evaporation and boiling. In both evaporation and boiling, the substance changes from the liquid state to the gaseous state. But what are the differences? The first difference between evaporation and boiling is that evaporation occurs at any temperature. This temperature is below the boiling point and may be at room temperature. Example of evaporation: laundry on a clothesline dries up by evaporation, so it occurs at any temperature. On the other hand, boiling occurs at the boiling point, which is specific temperature. For example, the boiling of water boils at 100 degrees Celsius. The second difference is that evaporation occurs at the surface of the liquid. So the surface particles only are involved, and in boiling it occurs to all the particles. All the particles are involved in the process. The third difference is that if we look at this example, we will find that water boils at 100, and we will find that boiling produces bubbles. Boiling produces bubbles. Does evaporation produce bubbles? No. So in evaporation, no bubbles. The last difference between evaporation and boiling is that boiling is a faster process, while evaporation is a slower process. Factors affecting evaporation. The first factor is the temperature. As the temperature increases, so here we have the temperature in the picture. We have A and B. In A, the temperature is higher than in B. So as the temperature increases, the rate of evaporation increases, or the faster is the evaporation. The second factor is the surface area. We have here 1 and 2. The surface area at number 1 is higher than the surface area at number 2. So the larger the surface area, the faster is the evaporation. The last factor is volatility. What is volatility? Liquids are classified into volatile liquids and non-volatile liquids. Volatile liquids like the alcohol, it has low boiling point. Non-volatile liquids like water. If we look at this picture, this is a picture of a bottle of alcohol. If the bottle of alcohol is left open at room temperature, the alcohol will evaporate and it turns from the liquid state to the gaseous state. So the volatile liquids evaporate faster than the non-volatile liquids. Changes in state can be shown on a graph. The heating curves and the cooling curves. The heating curve. First, we have to do an experiment to get the results to be able to plot the graph of the time versus the temperature. We need a source of heat, we need a beaker, we need ice, we need a thermometer and a timer. The first step is to place some ice in a beaker, measure the temperature of the ice and record it. So we measure the temperature and record it. After 1 minute, measure the temperature again and record it. Repeat every minute until at least 3 minutes after the ice has melted. Then plot a graph of time versus the temperature of the heating of ice. This is regarding the heating curve. The heating curve is a graph for time versus the temperature for the change from ice to water to steam. In other words, solid to liquid to gas. The time is in minutes and the temperature is in degrees Celsius. The time is found on the x-axis because the time is an independent variable. It doesn't depend on anything. While the temperature is on the y-axis because the temperature is a dependent variable. It depends on the time. So here, let's study together this graph and highlight the important points. So here, from A to B, then C, then D, then E, then F. Okay. As the temperature increases, the ice gains energy, the particles vibrate according to the kinetic particle theory, expand, and at point B, the ice starts to melt. So here, melting starts. At point B, melting starts, which is 0 degree Celsius. So at this point, we will find a mixture of solid plus liquid, ice and water. At point C, melting is complete. From B to C, we have a plateau, or in other words, the curve flattens. What does this mean? This means that the temperature here is constant. Even though heat energy is being put in, where does this energy go? So an important question here. Where does this energy go? This energy is used to overcome the forces of attraction between the particles. Then from C to D, the temperature increases till the liquid reach the boiling point, which is 100 degrees Celsius. So at point D, boiling starts. From D to E, the curve flattens, the temperature is constant. Where does the energy go? This energy is used to overcome the attraction forces between the particles. So between D and E, we'll find a mixture of a liquid and a gas. Then at point E, boiling is complete. And all the particles turn into the gaseous state. We have here steam or water vapor. The heating curve is used to determine the purity of a substance. Explain why. Look at this graph in front of you. This is a heating curve of water. Does it represent pure water or not? If we look at this graph here, we will find that there is no sharp melting or boiling point. So, is this a heating curve for pure water? No, this is not pure water because here the substance melts and boils over a range of temperatures. On the other hand, if it's pure water, we should find sharp melting point and sharp boiling point. But here we have a range of melting points and a range of boiling points. So this indicates the presence of impurities in the water. The cooling curve. The cooling curve is a mirror image of the heating curve. The same we have here, time in minutes on the x-axis, temperature in degrees Celsius on the y-axis. At point A, the gas starts to cool. The gas loses energy, and at point B, it starts to condense. So this is the condensation point. From B to C, the temperature is constant. The energy lost is used to build up the intermolecular forces of attraction. Between B and C, you'll find a mixture of a gas and a liquid. From C to D, the temperature decreases, and at D, the liquid starts to freeze. So here we have the liquid here starts to freeze, and this is the freezing point of water. From D to E, the temperature is constant. The energy lost is used to build up the intermolecular forces of attraction. So here we find a mixture of a liquid and a solid. From E to F, we will find only the solid phase, and it becomes regular pattern, the crystal lattice structure. Thank you for watching. Hope this was beneficial.